Okay, let's get started. All right, so today we're going to talk about Bayes nets, also known as graphical models, which are a technique for building probabilistic models over large numbers of random variables in a way that is efficient to specify and efficient to reason over. I think this is a really exciting topic because this is one of the main tools that we just didn't have in the sort of first go-around of AI in, say, the 80s. And it's not like people weren't aware of probability. It's not like people weren't aware that there was ambiguity and uncertainty. We just didn't have the tools we needed to manage and reason over uncertainty at scale. And one of the main tools that was developed was what we'll be talking about today. So in general, what we're talking about now is probabilistic modeling. In the first part of the course, we mostly talked about actions, selecting actions, sequence of actions, chaining reasoning along actions. And what we're talking about now is not so much about actions, but about beliefs. So you want to be able to describe how some portion of the world, some variables that you care about, how they work. And in a probabilistic setting, how variables work means how they interact in a noisy way with each other. So this is modeling. So there's going to be a whole bunch of math. We're going to talk about the machinery and the formalisms today, but this is modeling. And whenever you do modeling, you're in the game of making simplifications. So models are always going to be simplifications. Our probabilistic models are going to be simplifications. So we'll pick some random variables, and then there'll be some variables we don't model. So there are going to be some variables that just don't appear, either because we don't want to take the time to model them or we don't know how to model them. And it may be that even amongst the variables we have, there are interactions that are too minor or too expensive to capture. So whenever we talk about models, there's sort of the formulation of the model. Which variables do I include? Which interactions will I model? Where do I get those probabilities and how do I learn them? And that's tricky. Often there you're making judgment calls and trade-offs. And then once you have your model, there's the algorithms and queries you run against it. The formal questions. In this model, what is the probability of X given Y? And that's what we'll be starting to talk about here. And as we go, we'll try to sensitize a little bit the questions that occur in terms of thinking of trade-offs. I love this quote from George Box. All models are wrong, but some models are useful. And our job is to come up with models that are useful. Not really models that are exactly right, because only in rare cases can we model a domain exactly. And we'll see examples of that today. In the back of your head, think, what's the price of not modeling a domain exactly? The price is uncertainty. All the variables you leave out, all the interactions you leave out, they show up as noise on the other variables. And we'll see examples of that. So what are we going to do with probabilistic models? Remember, this is in the framework of rational AI, which means making decisions that maximize your expected utility. Part of maximizing your expected utility is inferring what's going to happen or inferring something about underlying causes given evidence. And so we, or really our agents, need to reason about unknown variables. And that usually takes the form of, given some things I do know, my evidence, and some things I don't know but I'm curious about, the query variables, and a model that connects them, what can I conclude? And that's what we'll get into today. One example of this is explanation. This is diagnostic reasoning. I see some symptoms and I want to know the underlying cause. Another example of this is prediction. This is causal reasoning. I have a model. I think, what will happen if I make this change? And then I play it forward. Okay? And that seems like simulation. And in a way, it sort of is noisy simulation. Another kind of thing that we'll see probably in about 2 weeks, another use we can use these probabilistic models for is value of information queries. And that's for things like, remember in Ghostbusters, I could probe and gather information, or I could act, and there was a trade-off between gathering information and making a decision. And so you have questions like, how much, whether it's in dollars or utilities, how much value is there in finding out this piece of evidence? Those computations where knowledge is associated with gains in utility are really a fundamental thing in rational decision making. And those are called value of information computations. And we'll take a look at that once we have all of the machinery. And that's going to be, I think, a really cool lecture where we connect the action decision making up to the probabilistic inference. Okay, any questions before we get started? Okay, so we're going to, in some ways, continue where we left off in the past lecture, talking about probabilistic models, which are formally joint distributions over a collection of random variables, and talking about properties of those models and computations we can do over those models. One major property that's going to be really important today that we didn't get into last time is the notion of independence between random variables, and then following on to that, the more important notion of conditional independence. So we say two variables in a joint distribution are independent if the following holds. So informally, two variables are independent if there's no interaction between them. That's an informal notion. What does that mean mathematically? It means that if I take a distribution P of x, y, and remember that's a big table that tells you for every value of x and y, how likely that outcome is, and that's going to be the probability of that outcome. If for every x and y, the probability that x and y happen together is simply the probability that x happens, nothing said about y, times the probability that y happens, nothing said about x. Now, this is, in general, doesn't hold, right? What do we know in general? We know in general that P of x comma y, the probability of x and y, is the probability of x times the probability of y given x, right? That's always true. That's the product rule, okay? We saw that last time. But you might have a very special distribution in which y, in fact, doesn't depend on x at all, and the joint probability is equal to the product of the marginal probabilities. What this says is that this joint distribution, which is a big two-dimensional table, factors into the product of two simpler distributions, here two one-dimensional tables. And that means it's a special kind of simple distribution. Here's another way you can write that. Another way you can write this is just what we showed up here, that if it's true that the joint distribution factors into the product of the marginals, it's going to be true that for all x and y, the conditional probability of x given y, that is how likely x is to take a certain value given a value of y, is the same as its marginal probability. That is, learning something about y doesn't change my belief in x at all. And if that's true, then we say x and y are independent. We write that this way. That little thing between x and y, you can think of that as a sort of perpendicular sign. It says they're in some deep sense they're independent. They're doing their own thing, so that looks like a perpendicular sign. Okay? Now, independence is our first example of a modeling assumption. I can take two random variables like coin flip 1 and coin flip 2, and I can ask what is their joint distribution, or I can make an assumption. I can say, you know what? I know enough about how coin flips work that I'm going to assume they have nothing to do with each other, and I can think of them as being governed by independent distributions with no interaction terms, which means if I want to know their joint probability, I multiply their independent probabilities. Okay? There's a couple reasons why independence might not hold. One is that there are often very subtle interactions or weaker interactions. You may choose not to model them, but there are often these sort of like lower order interactions. We'll see some examples of that today. And of course, if you actually look at a joint distribution that comes from data, often there's going to be imperfect independence. So if I flip coins a couple of times, they might not exactly fall independently. That would be something that would only be true in the limit. So let's take an example, and this we'll do intuitively. Let's say we have a domain which has the following random variables. Weather. So what kind of weather is there? Traffic. How much traffic is there? Maybe that's been discretized into light traffic and heavy traffic. Cavity. This represents, do I have a cavity in my mouth? And toothache. Do I have a toothache? So here's 4 random variables that I may care about. And if I build a probabilistic model over them, we might be able to simplify that model. Instead of being a big 4-dimensional giant table, I might be able to split it into 2 tables where parts of my domain don't interact. So what's a good split? Or maybe all these variables maybe are independent. Are there any variables there that probably aren't independent? That's an example of things that are not independent. One is weather and traffic. There's probably some correlation there. Weather gets bad, traffic gets bad. Okay, those aren't independent. How about cavity and toothache? Independent? No, go see your dentist. Dependent. All right. But these 2 subsets of variables maybe don't have any major interactions. And so I might say that the variables weather and traffic, although they interact together, they may be governed by one distribution. Cavity and toothache are governed by another distribution, and there maybe don't need to be any interaction terms. So if I want to have the probability over all 4, I can write that as the product of the probability of the 2 pairs. Okay? That's the idea behind independence. Let's do an example. Here is a Here is a joint probability distribution over the variables t and w from last time. Remember, t was either hot or cold, it was the temperature, and w was either sun or rain, it was the weather. And here's some probabilities. There are many probability distributions over these variables. They all look just like that, but with different numbers. And of course, they all add up to 1, they're all positive, that kind of thing. Now what I can do is I can compute the marginal over t. So I can say, well, t is either hot or cold. And if I want to know what's the total probability of t equals hot, I look at my joint table, I look at all the consistent rows, and I add those together, and so I get 0.5, and so I can compute this. We did this last time. This is projecting a joint distribution over the two variables onto a marginal distribution over just one. And of course I can do that for p of w too. And I look in there and I do my computations, and I see that the total probability of sun is 0.6, for example. Okay, so P1 here on the left is a joint distribution over these variables. PT and PW are marginal distributions of that joint distribution. So these are derived. Okay? Now I can ask a question, which is, what is the probability of hot, sun? Well, I can look it up in my table in P1, and I see, oh, it's 0.4. Okay. So in P1, that's 0.4. In a distribution in which these distributions T and PW were the marginals, and where independence held, I would know that P of hot, sun is equal to P of hot, the marginal, times P of sun. And so I can look those up. Well, here's P of hot, here's P of sun, and that's 0.3. What do we know? We know that P1 is not a distribution in which T and W are independent. And in general, things aren't independent. If I grab an arbitrary probability distribution over some variables, things won't be independent. Only a simple subset of them are. For example, here's P2. In this one, P of hot, sun is 0.3, and if you check all the other entries, you'll see that that definition of independence holds. The product of the marginals is equal to the joint for all of those different outcomes. Okay, so P2 and P1, just to sort of exercise some brain muscles for next time, P2 and P1 are two different joint distributions over the same variables. P2 has the property that T and W are independent. P1 does not have that property. So in some sense, P2 is simpler. One way in which it's simpler is I can write it by just supplying you P of T and P of W and giving you the information that I'm thinking about the independent distribution. So it's more compact. Any questions about that? Yep. Okay, so there's a couple of important things here, and let me kind of split them apart. One, I'm giving you probability distributions. I'm not telling you what data you learn them from or what sampling error there is or any of that. We will get to that later. Right now, these are simply two probability distributions. They have different parameters. One of them is independent, and I can verify that. That's P2 by checking these equalities, and P1 is not independent. And what that means is T and W interact in P1. So, for example, as we can see, if hot and sun don't interact, the probability of hot and sun is 0.3. Hot and sun do interact in P1, and so the probability is 0.4, and so there's a correlation there, right? And you might informally say that correlation is it's more likely to be hot if it's sunny. Okay. The sampling question is a good one, and we'll get to it later. All right, here's an extreme example of independence. Let's say you are an octobot, and you're flipping a whole bunch of coins, and you're flipping n coins. And you want to describe this kind of mathematically imaginable giant joint distribution over these n variables. It's of size 2 to the n, because for every sequence of heads and tails, there at the end is the probability. But of course, we know that when you flip a coin and you flip another coin, those things are independent. And so there's no need to actually ever write down this giant exponentially large distribution. I can instead just write down each of the n marginal distributions and arm you with the knowledge that in my model, these random variables are independent. And then if you ever ask me a question from the full joint distribution, we can just multiply together the pieces and get the answer. Okay? In fact, it could be even more compact than this. Because in addition to being independent, these coins could also be identically distributed, which means I only have to give you one probability distribution, and then you can imagine replicating it. Okay? But this already is an exponential speedup. This thing on the bottom is of size 2 to the n, and this thing on the top is just of size 2n. So that's a lot better. Okay? All right, so independence is great. It lets us take a multiplicatively large table and break it into smaller pieces. This should maybe remind you of something in CSPs, how much easier those CSPs were if I could take my big CSP, break it into smaller CSPs, and solve them independently. But, we'll bring back the mouth in a second. But just like in CSPs with where we talked about subproblems that completely don't interact, it's also the case that independence, probabilistically, is very rare. And it's very rare for a couple reasons. One, variables do tend to have interactions, but in particular, when you choose to build a model of something, you typically throw in all the variables that you care about, and those are the variables that interact. Yes, it's true that weather and traffic don't interact with cavity and toothache, but they generally don't show up in the same model either. So in general, all of your variables do have some degree of interaction, and independence is too strong a notion. But it's the building block of something that we can use efficiently, which is called conditional independence. So in conditional independence, we don't go so far as to say that two random variables have no interaction. What we say instead is that their interaction is sort of mediated by another variable. And the way we write that formally is rather than saying that the joint distribution is a product of marginals, we have some other simplification of the chain rule that is less radical. So for example, if we take the variables, okay, so imagine you are building a dentist robot, okay, and it's going with this little probe and it's poking at your teeth. And the random variables are, do I have a toothache or not? Do I have a cavity or not? And will that little probe catch on a hole in your tooth? So these are three random variables, and for three variables, I could imagine just having a full distribution. Okay, it wouldn't be that big. But I might be able to do better than that. Okay, because somehow it seems like if I have a cavity, my tooth might hurt or it might not, but if I have that cavity, whether or not the probe physically catches on my tooth maybe doesn't have much to do with whether or not I'm feeling pain. Okay? And if that's the kind of simplifying assumption you can use via conditional independence. So I could make an argument in this domain that goes something like this. If I have a cavity, the probability that the probe catches in it doesn't depend on whether or not I'm experiencing pain. What is that formally? Formally, that's saying the probability of plus catch given the toothache and the cavity is just the same as the probability of the catch given the cavity. Somehow, the toothache doesn't add any information. So the conditional probability of catch given toothache and cavity is the same as the conditional probability of catch given just cavity. Okay? Now, in an actual joint distribution, this could be true or not. You could go check. You could go churn some numbers and check. As a modeling assumption, I could say before I even get a probability distribution, I want to assume this to simplify my life and make my distribution more compact. Now, that same independence would have to hold even if you don't have a cavity. So in this case, well, if I don't have a cavity, there's some probability that the probe will catch anyway. Now, the question is, what's the probability that the probe will catch if I don't have a cavity, but for some reason I'm experiencing tooth pain? Well, you don't have a cavity, so who knows why you're experiencing tooth pain, and you might make the assumption that those conditional probabilities are the same. What does this mean? This basically means that once you know about cavity, you know all you need to about catch, and the toothache doesn't matter anymore. Is that independence? Well, it's not independence, because it's not the case that the catch and the toothache are independent. If that were true, if I learned that I had a toothache, it wouldn't change my belief of whether or not the dentist would find a catch. But it should change my belief, right? Because the toothache maybe means I have a cavity, which in turn maybe means that there's going to be a catch, but there's not a direct connection. That's formalized by these equations. What we say here is we say that the random variable catch is conditionally independent of toothache given cavity. That's much weaker than being completely or marginally or absolutely independent of toothache. It's only once you know cavity there's no sort of correlation left between them other than what was mediated by that variable. So if these properties hold, we say catch is conditionally independent of toothache. And there's a bunch of ways to write that statement which are all mathematically equivalent. Conditional independence is an assumption. It may or may not hold in a given distribution. And when you assume it, you simplify your distribution. But that same assumption can be written in a lot of ways. One is this way, what's above, that if catch given cavity is the same as catch given cavity in toothache. But you can write it the other way. You can say the probability of toothache given cavity is the same as toothache given cavity and also knowing about the catch. You can also write it like this. I actually really like writing it this way. This way says that once I know the value of the cavity random variable, whether it's plus or minus, the remaining distribution over toothache and catch, that distribution is independent. So toothache and catch, you can think of that as its own little distribution over two variables conditioned on cavity. And if that little distribution itself is independent for that conditioning environment, then you have conditional independence. Each of these can be derived from the others. You can go apply your definition of conditional probability and cross stuff out and show that. Okay? Yep. That's a great question. So does the knowledge that, let's write this somewhere. So I could write toothache is independent of catch given cavity. Does that imply that toothache and catch are not independent? Not necessarily. I could go back to my coin flips and I could say coin flip 2 and coin flip 4 are independent. Yep. Are they also conditionally independent given coin flip 3? Yes, but you know something stronger. So in general, we want to use the strongest assumption we can make, but just because you have one assumption doesn't mean that other assumptions are not simultaneously true. Okay, so we already talked about this. Unconditional or what's called absolute independence is very rare. On the other hand, conditional independence is one of our most basic ways of saying something about a probabilistic model that simplifies it in a way that allows us to tractably compute important quantities on large distributions. So independence, rare in theoretical, conditional independence, very important. Okay, and we'll see conditional independence and its consequences a lot today. Okay, so mathematically, if I have a distribution over three variables, x, y, and z, and I say x is conditionally independent of y given z, what that means, what that has to bottom out is this statement. For all values of x, y, and z, so you would have to check the whole distribution. You go down, check, or prove it to yourself mathematically. If you wanted to verify this property holds on a distribution. So for all x, y, and z, the probability distribution over x and y, or the probability of x and y given z, is equal to x given z times y given z. So if you ignore z there, that's independence. But since that independence only holds when z is known, it's conditional independence. This is another way to write it. This says for all x, y, and z, the probability, your belief over x, given your knowledge of z and y, depends only on what you know of z. Okay? This says that if you already know z and you have some belief over x and you learn something about y, your belief should not change. Okay. All right, let's do some practice. We're going to come back to these toy domains, I think 3 times today, depending on how far we get. So let's think about a domain with the following random variables. Traffic, t, that's how much traffic there is. Umbrella, whether or not I have an umbrella, or whether or not I observe an umbrella on my robot. And then raining, whether or not it's raining. So are any of these things independent? You look and you say, oh, well, the umbrella and the traffic don't have any kind of correlation. Well, that doesn't sound right, because if I see the umbrella, I might think, maybe there's going to be traffic too, because maybe it's raining. Okay, so nothing's actually going to be, it's probably a too strong an assumption, and maybe not a useful assumption, to assume independence. But what could we assume is conditional independent? Two variables that may interact, but that interaction is completely mediated by a third. Any votes? Yep. I guess I'm looking for a statement of the form, something is conditionally independent of something else given some third thing.
I was thinking that the probability of seeing an umbrella given that it's raining and there's traffic is the same as the probability of seeing an umbrella given that it's raining.
Okay, so that's the presence of umbrellas and traffic on the freeway are conditionally independent once you know whether or not it's raining. So let's think what that means. That means if I know it's raining, well, traffic is likely and so are umbrellas, but not in a correlated way. It's not like when it's raining and the umbrella comes out, suddenly everybody's like turning their head to see the umbrella and that causes more traffic. There's not an additional correlation. And you say, well, wait, but what you said is a little weird, but maybe possible. Yeah, there's always going to be, there's always conceivable additional interactions that you can declare too minor to be modeled. And of course, we could quantify what too minor to be modeled means in terms of sort of information gain and things like that, but we're not going to do that today. Okay, so for today, it seems reasonable to say that traffic and umbrella are not marginally independent, but they seem to be conditionally independent given rain, and that is an assumption we can make to simplify our model. And you say, well, how exactly does that simplify my model? I thought you were just handing me giant probability distributions. Today we'll see how it simplifies your model by allowing you to specify it in a more compact way. Okay? Okay, let's do another one. Here's this model. F is whether or not there's fire, S is whether or not there's smoke in the room, and A is whether or not the alarm goes off. Now in this one, maybe it's tempting to start thinking about things causally, which can be misleading, but often helpful anyway. So let's think of, are there two variables that maybe have some interaction, but only mediated by another one? Anyone want to make an assertion that something should be conditionally independent of something else given a third variable? So let's first think about what caricature I have of this robot fire alarm situation. It's that the standard way these things work is there's fire or not, and if there's fire, that fire has smoke, and that smoke gets into the alarm, and the alarm has a smoke sensor and goes off. And maybe that's all a noisy process. This alarm doesn't always go off. Sometimes it goes off anyway. Okay, so now what can I say about these variables? Well, yep.
The fire and the alarm are conditionally independent given smoke.
Yeah, so it seems like a reasonable statement. I could say, well, the fire and the alarm are certainly not marginally independent. That's the whole point of a fire alarm, is when the alarm goes off, it makes you worried that there's a fire. That's the point of the alarm. But if the mechanism is via the smoke, then it may be that if I put smoke into the room, and I know I've put smoke into the room, now suddenly there may be no additional correlation. And you say, but what if the fire alarm also had a temperature sensor? Well, okay, then this is a poor model now. So here's an assumption that may make sense to make or not based on what is actually going on in the world and how closely I want to model it. Okay. Let's think about how conditional independence, which so far has been a relatively intuitive concept, let's see how that's going to anchor into expressions we can write about joint probability distributions and ways we can write them using the chain rule. So remember, the chain rule says that if I have n variables and I want to talk about the probability of some assignment to those n variables, one way I can write that as a product of other probabilities is I can say, well, it's the probability of x1 taking on whatever value it takes on, times not the probability of x2 by itself, but the conditional probability of x2 given x1. So given what I already have at x1, I extend that to x2, and similarly times the probability of x3 given everything that precedes it in that ordering of variables. This is always true. And remember, this was true because you could think, here's probability of x1, but the probability of x2 given x1 was just p of x2 comma x1 divided by p of x1. And then the x1's canceled, and this whole thing sort of telescopes. So that's no assumption. That's just the chain rule. That's always true. And by the time you get to the n to xn, it's xn conditioned on all variables preceding it. So not super helpful. Okay, so the trivial decomposition here of traffic, rain, and umbrella is that joint probability can be rewritten as the product of probability of rain times the probability of traffic given rain times the probability of umbrella given traffic and rain. This is always true over any distribution over 3 variables. But we decided something. We decided that for the purposes of our model, it seemed reasonable to assume that the probability of umbrella given rain and traffic was the same as the probability of umbrella given just what? Okay, given just rain. Because umbrella and traffic were conditionally independent given rain. And if we make that assumption, now that joint probability is equal to the product of these simpler conditional probabilities. And now we're starting to get somewhere. Because now I have a way of talking about a large, potentially exponentially sized joint distribution as a product of little pieces that don't just keep growing and growing and growing. In the chain rule, by the time you get to the end, these conditional families are just as big as the joint distribution. But not anymore, because they're not getting more complicated as I go. Okay? So now I finally accomplished something from the simplification, which is I can specify entries of a joint distribution using products of simple probabilities, and how simple they are depends on what conditional independence assumptions I can make. Okay? So what we're going to do now is we're going to get into Bayes nets, which are also called graphical models, which are a tool to help us express conditional independence assumptions and think about them in a graphical way, which can both help us design algorithms and also help us sort of think about these probability distributions in new ways that has been helpful. All right. Let's think about Ghostbusters. So remember, this is the tiniest Ghostbuster board. It's got 2 squares. That means the ghost is in either the top square or the bottom square. So that's it. So one random variable is where's the ghost? And I could phrase that as ghost location or true false ghost is in the top. That's going to be the random variable G. Let's say it's uniform marginally. Here's 2 other random variables. Remember, we took sensor readings, and let's imagine the sensors just say red or not red, where red means close. Okay, so I could have random variables B and T, which are the reading in the top square, could be red or not, it's noisy. The reading in the bottom square, could be red or not, it's noisy. Okay, and my sort of verbal description of this model is each sensor reading depends only on where the ghost is. What that means is the 2 sensors, they're certainly not marginally independent, because if I read red up top, I'm probably not going to read red on the bottom, and if I read red on the bottom, I'm probably not going to read red up top. So they're certainly not marginally independent. But it's reasonable to say that they're conditionally independent given the actual position of the ghost. Okay, that is, if I know where the ghost is, now these are just noisy sensor readings that aren't correlated. And you say, well, but they could be correlated because what if your sensor's sometimes busted and then it reads red everywhere? Or what if, the first time you read red, it blows out the red light and now you can't read red anymore somewhere else. So you could imagine correlations, but the basic idea that there's an underlying variable with independent measurements seems appropriate for this domain. So what does that mean? That means we're given the following thing. So I can tell you, hey, the probability that the ghost is in the top versus the bottom is 50-50. These are givens. I could also tell you the probability of a red reading if the ghost is at the top is 80, but the probability of a red reading given the ghost is in the bottom is only 40%. Okay, so this does not fully specify a joint distribution over all these variables in general, but it's enough to specify the full joint distribution if I have conditional independence. Well, why is that? That's because if you come along and say, hey, I'm curious about this entry of the joint distribution, I have some value of T, B, and G, well, in general, I know that I could look that up by telling you, how about I find P of G, I have that here. And how about T given G? Okay, I have that here, so far so good. The chain rule demands B given G and T. That's what the chain rule requires. I don't have that. So I can't compute this entry you asked for in the joint distribution. Until conditional independence to the rescue, if I assume that B and T are conditionally independent given G, meaning the sensor readings are conditionally independent given the ghost position, then I know that's the same as that without the T, and suddenly now I have the right variable, the right parameter to plug in. Which means with those givens on the bottom, and the assumption of conditional independence of the sensors, now I can fill out this whole table, and now I can do all of the computations that I did last class, like compute how likely is it that the ghost is at the top, given that they both read, or something like that. Okay? Okay, so Bayes nets. What's the big picture? Yep. So are you asking how do I know that? So the assumption here that really lets me go here is that T is conditionally independent of B given G. Are you asking how I know I have that assumption, or how does having that assumption unlock the joint distribution? Yeah. So this is as modelers. As modelers, we have to sort of take the information we have about the problem, which in this class will usually be specified in words. Like we'll give you some word problem or appeal to some sort of fairly clear causal structure where you can kind of tell what is directly dependent on what, and translating that into conditional independence. So what I would have to tell you is that I have to tell you I'm imagining a case where I have sensor readings, and those sensor readings are conditionally independent given the underlying variable. Because like I said, if I could come up with some story that makes that conditional independence no longer reasonable to assume. So another way to think about it is the givens are various collections of conditional probabilities along with conditional independence assumptions. Sometimes we state them in words, sometimes we'll just lay them out in symbols. And the point of this slide is that when you have the right givens, along with the right conditional independence assumptions, you've unlocked the joint distribution. You can build the whole thing, when you wouldn't have been able to simply according to the chain rule. And that's really important because it means that under the right circumstances and with the right conditional independence assumptions, tiny little pieces of probability distributions can imply an entire joint distribution, which will unlock the ability to take lots of little pieces, assemble them and reassemble them, and then produce some other little piece without ever having to construct the whole large object. Yep. So the question is, why do we have so much emphasis about finding the whole joint distribution? We won't forever, but right now the only algorithm we have for answering an arbitrary query in a domain is by starting with a joint distribution and doing computation on it to answer our query. And so we're like tiptoeing towards the ability to start with small pieces, build the whole joint distribution, and then collapse it again into a different small piece. Where we'll eventually get is algorithms that help you avoid inflating the whole thing if you don't have to. And so you sort of manage assembly and projection in an interleaved way. And that's going to be, for example, the variable elimination algorithm. Great questions. More great questions. Yes, so conditional independence is not an ordered notion. Okay. All right, so what's the big picture of Bayes nets? Bayes nets are a device for describing a complex distribution over a large number of variables, where that large distribution is built up of small pieces, meaning local interactions, and the assumptions necessary to conclude that the product of those local interactions describes the whole domain. Okay? So it's going to be our way of describing big, complicated domains using tiny pieces. And there's really sort of a deep analogy here to CSPs, where we described the interaction amongst many, many variables in terms of lots of little local constraints. That didn't mean that there weren't correlations between what was assignable at various places that were more distant, but what we described was the local constraints, and then there were global consequences. Bayes nets are the same. We're going to describe lots of little local interactions, and there's going to be global consequences that will allow us to do much more complicated kinds of inferences. Okay, so up till now, as was just pointed out, we've been talking about a probabilistic model being a full joint distribution. Mathematically, that's great. That full joint distribution, it's exponential in size, but it describes all the quantities we care about. But there are some major problems with using joint distribution tables as models. One is, it's too big to write down. And secondarily, even if you could somehow write it down, it's really slow to do computations over exponentially large things. Okay, that's sort of a computational space and time cost. There's another cost, which we don't always think quite as much about in computer science, but is very important in AI, and that is a statistical cost. The bigger a thing I'm trying to learn, the more parameters I'm trying to learn. You can think of the parameters, the entries of those probabilities, as being facts about the world that I learned through observation, right? The more parameters I'm trying to learn, the more data it will take to learn that. And so if I'm trying to learn this really, really large thing where every row is sort of its own thing that must be learned, that's going to be very expensive. Whereas if I can say that whole large object is really described by a couple of simple interactions that chain together, now suddenly I just have to learn those pieces and things become much more what's called sample efficient. And actually, you'll see this in your projects already with reinforcement learning, where with just naive Q learning, you have to learn about every possible state of the world, but with function approximation, you only have to learn about the aspects of those states that generalize in a much better way. It's the same kind of thing. So what are Bayes nets? Bayes nets are a technique for describing complex joint distributions, which are models of a domain, using simple local distributions. In this case, those will be conditional probabilities. These are also called graphical models, and what we do is we describe local interactions between variables, and we do it in a very careful way that those local interactions imply a distribution over the entire set of variables. We'll be a little vague about those interactions for a little bit, and then we'll get concrete. Okay? So let's do some Bayes nets. I'm going to show you some examples, then we're going to think up some examples, and then I'll actually pull out a Bayes net and we'll look kind of under the hood and see what's really going on. So here is an example of a Bayes net that describes an insurance domain. And so there's a lot of variables in the insurance domain. And of course, one of those things at the bottom are going to be various costs that you might want to predict if you're an insurance company. This one's for vehicle insurance. And then there's going to be various other things, like things you know, like the age of the driver and the mileage on the car. And there's going to be things you don't know, like the skill of the driver or whether or not there's an anti-theft device or the socioeconomic class or something like that. Okay? This Bayes net is a description of that domain, which includes a decent number of variables. Okay, that's like, something like 30 variables there. And if each of those variables had 10 values, like maybe 10 age buckets and 10 mileage buckets or something like that, a full joint distribution over all of those 30 variables with 10 values each, how many entries in that joint distribution? That's each variable has a choice of 10 things. So it's going to be 10 to the 30th. 10 to the 30th numbers is bad news. Okay? But it's even worse if you had to somehow examine 10 to the 30th case studies in order to figure out what those numbers even are. Okay, so joint distribution, conceptually really, really big. But what this Bayes net also shows is what the direct interactions are. So for example, there may be a correlation. Let's find something interesting here. Let's think, if you're an insurance company, let me change colors. If you're an insurance company, you might care a lot about this variable. Accident. That seems like something you want to predict. That's probably correlated with the age of the driver. And in some way, it's probably correlated with the year of the vehicle and whether they have an extra car and what their home zip code is and all of those things. But what this network does is it says, actually, you know what? The accident is really only directly determined by the quality of the driving and some factors about the car for accident prevention, like anti-lock, anti-lock brakes and so on. And you say, of course, well, how does that connect to everything else? Well, that driving quality is determined by the skill of the driver, but also their risk aversion. Like if you're a really good driver, but you take lots of risks, that's not the same quality of driving as if you're a really good driver and you don't take risks. And so in specifying these little pieces, that can finally connect up to things like, for example, the age or the mileage on the car and so on. Okay? So this isn't the whole story for this domain. There's also the question of what exactly is the dependence between age and driving skill, which isn't on the slide, and I have no idea. Hopefully some insurance company knows. Okay? But what this does is it lets us do things like observe quantities like age and the vehicle year and the zip code and whether it has airbags and conclude things like how likely is there to be an accident. Okay? That's one use for a network like this. And because all we have are little local connections between variables, we don't need anything so expensive as 10 to the 30th to specify it. Okay? This might be a network that you use for simulation. I know this. Is there going to be an accident? And you're sort of computing on the basis of evidence up here, or initial state up there, you're computing what might happen and with what probabilities. That's sort of computation going downward in the network, where you might query something low in the network. Here's an example where it might go the other way. You want to have a robot mechanic, and so there's going to be evidence down at the bottom of the network here and some underlying causes of why the car might not start, like the battery could be dead or the alternator could be broken. And so you might do things like, diagnose, like, are the lights, is there an oil light on? What does the gas gauge read? What does the battery meter read? Will the car start? And so on. And so what you can do in this network here is you observe some of these things at the bottom and you can do some inference over what causes there might be. Now, rather than exactly knowing the probability of any mapping from causes to effects, we only know little things like, when there's no oil, the oil light turns on except when there's no power coming from the battery, or something like that. And so a network like this can help us do diagnosis, and also importantly, it can encapsulate a lot of knowledge about cars. This network probably knows more about cars than I do. That's maybe more comment on me. Okay, so graphical model notation. What are graphical models? This is going to look a lot like CSPs. What are graphical models? Well, they have nodes in them. They're going to be graphs. So they're going to have nodes in them. Those nodes represent variables, and those variables have domains. And they can be unassigned, which is called unobserved, or they can be assigned, which is called observed, just like in CSPs. There are arcs, and the arcs represent interactions between variables. Again, just like CSPs. CSPs, we would say something like, hey, these two variables, this one has to be greater than that one. I'll put a constraint between them. It may have other effects when it chains together with other constraints, but that's my local interaction. There's going to be local interactions here. And we'll see in a bit what those local interactions are. Okay? The arcs indicate something like direct influence between variables. Formally, they're encoding conditional independence. Okay? But it can be very convenient to build up your intuition to think about the arcs as encoding causality. We'll see that that's not actually true. They don't actually need to, and they're not guaranteed to encode causality, but often that's what ends up happening. So here's an example of a Bayes net for a model we already know. For cavity, toothache, and catch, we see there's a direct influence between cavity and toothache, and another direct influence between cavity and catch, but no direct influence between toothache and catch. The influence between toothache and catch is mediated by the path that goes through cavity. And paths in this graph are going to be very closely related to conditional independence. So nodes and arcs. Nodes are variables, arcs are interactions. For now, think of the arrows as causes. Cavities cause toothaches, and they also cause catches, but toothaches don't cause catches, and so I don't have an arrow there. Okay. I think what we're going to do is we're going to take a 2-minute break now, and then we will come back and see examples of first simple and then increasingly complicated Bayes nets, and then we'll peek underneath the covers and see what those Bayes nets are defined by in addition to the graph. Okay, 2 minutes. Okay, let's see some examples of Bayes nets. Okay, first one, back to our independent coin flips and independent coin flips. With no interactions between the variables, we're going to have absolute independence. And the Bayes net that corresponds to that will be a bunch of variables with no arrows between them. Okay? And as we'll see later when we dig a little deeper into this, disconnected things in the network, just like they did in CSPs, correspond to independent subproblems, and here that means absolute independence. Okay, here's a simplified traffic domain. Variables are, is it raining? T, is there traffic? So what might we do? Well, here's one graphical model. Here's one Bayes net over those variables. This is the independent one. This one says, in my very simple model, these two variables don't interact, so they're going to each, it turns out, have a marginal distribution, and that's all you know. Here's another model. In this model, I have an interaction. This model says there's R and there's T, and the behavior of T is now a function of the behavior of R. So we are now capturing in this model, and I'll be precise in a bit how that's captured, we're now capturing a direct interaction between R and T. Okay, they are both valid graphical models or Bayes nets over this domain. But model 2 is probably better. The reason why model 2 is better is because an agent that's armed with model 2 can do things like see traffic and conclude something about rain, or see rain and conclude something about traffic. Once you start taking too many arrows out, as you gather evidence, you don't actually have the ability to update your belief over variables that you care about through connections to the evidence. And that's sort of the whole point. You want to see evidence and then infer something about other variables. All right. Let's do a bigger traffic case. This is going to have more random variables, and we will build a graphical model as we go. As I draw this model, I'm not being precise yet about the mathematical semantics of the model. We'll get that in a couple slides. For now, just think about the arrows as being causal or direct influence. All right, so let's add some variables to our traffic model. First variable, traffic. Okay, I'll stick that there. There's either traffic or there's not. Second variable, rain. Where should that go? Should it be separate? Should it point to traffic? Should traffic point to rain? Think causal for now. Does traffic cause rain or does rain cause traffic? To the best of my knowledge, the rain causes the traffic. Okay. Low pressure. The barometer has a low pressure reading. What do you think? Okay. We can put L up here pointing to rain. Well, they're certainly correlated. Now you could be like, wait a minute, a reading on my machine doesn't cause it to rain. So there's the actual low pressure, then there's the reading of the low pressure, which actually is L pointing to that thing. So we could get more and more fancy, but imagine this is the actual low pressure in the sky. All right. My roof is dripping. How does that fit into all of this? So it seems like rain causes that. All right. Does anything else cause that? Does the low pressure cause my roof to drip? Kind of. I mean, unless it's like really low pressure, like rips the membrane off my roof or something. Like it's that's mediated by the rain. Similarly, like does traffic cause my roof to drip? Like probably not. So this is a reasonable model. There's a ball game. How does that interact with any of this? All right. So ball game causes traffic. Any other interactions? Certainly doesn't cause my roof to drip. Anything else? This is reasonable, yeah? Yeah, that seems reasonable too. So here's an arrow that I could include or not. That would be a modeling assumption. It seems reasonable that rain affects whether or not the ball game happens. If I omitted that, I would have a slightly simpler model. And there's always a trade-off between how powerful your model is and how hard it is to work with. Okay, cavity. How about cavity? That's probably just out there somewhere, right? It's probably that's a separate process. It's the dental process over there. Okay. All right. Are there other graphical models I could draw? Yes. As I move arrows around and delete them, the set of conditional independence assumptions changes, and the set of probabilities I need to specify the behavior of the model will change too. Before I had this, let me change its color. Before I had this green arrow here, I didn't have the burden of specifying how ball game relates to rain, and now I do. On the other hand, now my model's a little bit higher resolution. Okay, alarm network. Here's the deal. The variables are, there may or may not be a burglary. Let's stick that in here somewhere. Okay. My burglar alarm goes off. Where does that go with respect to B? Well, they seem correlated. And if we're going to go in the causal direction, maybe the burglary causes the alarm. What about my neighbor Mary calls? Okay, let's put Mary over here. Is that connected to all of this? Well, it depends, right? We're now making assumptions about the model, but what are some reasonable ones? Okay, one is Mary's in France, she just calls sometimes. This is appropriate now. She may or may not call, it's disconnected. Might be that she calls if she hears the alarm. It might be that she's like staring at my house through her window and she'll see the actual burglary and she might call even if there's no alarm. If there's a burglary, then I need an extra arrow. Okay, here's John calls. So that's another variable. That may also be called because of the alarm itself. But if John's calling because Mary calls John first before she calls me, then I need another arrow from M to J. Earthquake. Where's earthquake go? We would have to say what we're assuming about this. One answer is the earthquake can set off the alarm, and only because of the alarm do my neighbors call me. Another could be earthquake directly causes everybody I know to call me, and then there would be direct arrows from E to J and M. Okay? So you see sort of these are modeling choices. In this class, we often give you a model or clearly state the assumptions and say draw the model, and then we have to compute with it. Okay. All right. So now we're to the key bit. We're to the semantics of a Bayes net. So what's this about? We just saw a sort of intuitive example of building at least the graph part of a Bayes net and thinking about arrows as capturing direct influence. And now what we're going to talk about is, for a given Bayes net, what does it mean? What joint probability distribution does it encode? And how do we know that? So, here we go, the full definition. A Bayes net is a set of nodes, one per variable x. Okay, so every variable in the network, every variable in the graph is a variable in the joint distribution. I have a directed acyclic graph over those nodes. So there are arrows between them, and there are no cycles. And if you think about that intuitively for causality, that makes a lot of sense. Like, you don't have like the rain cause the traffic, and the traffic cause the ball game, and the ball game cause the rain. That would be very confused. But we'll see mathematically that this acyclicity, meaning there are no directed cycles in the graph, bottoms out in the chain rule. It's because in the chain rule you introduce variables one at a time in some order. The fact that your graph has no cycles means there is an order that corresponds to the network. Okay, so a set of nodes, a set of arrows between the nodes that have no cycles in them, and hidden inside each node is a little conditional distribution family. So if you peek inside a node, there are a bunch of conditional distributions that describe the probability of that variable as a function of its parents, meaning for every setting of the parent values, there's a distribution. So if I look at this node X, I see it has these parents A1 through AN. That means if I peek inside X, there's a probability distribution over X, but not just one. There's one for every setting of the parents A. So if you have a lot of parents, there's a lot buried in this node. So the more parents you have, the amount that you have to stuff in that node to describe what X is going to do as a function of the parents, it grows exponentially. Okay, we often see this abbreviation CPT as a conditional probability table. That's what lives in the nodes. You can think of this as a description of a noisy causal process. It says, what is X going to do given A1 through AN? So you might think, what is a causal process? If it rains, then there's traffic. Okay, we could do that with logical rules. But here it's more like, if it rains, then there's a 90% probability of traffic. If it doesn't rain, there's a 30% probability of traffic. And because we need to specify the response of a random variable for each conditioning environment of the parents, we can think of this as a noisy causal process. Okay, so a Bayes net is a topology, meaning a graph, plus all the little local conditional probabilities that live inside the nodes. Okay, we'll see some examples, and then we'll build one of our own. Any questions? It's a good question. So the question was, couldn't you also express that one variable makes another less likely? You can express any conditional relationship. So you could say that rain makes traffic more likely. You could say brushing teeth makes cavities less likely. But in general, things aren't Boolean. So you could also say that the driver being of age 20 to 30 changes the driving quality distribution in the following way. It's an arbitrary relationship between the parents and the distribution over the child. And that's actually important. Okay? It's important because all these arrows tell you is sort of that there is a conditional probability table for each of these values. It doesn't tell you which table. So when I draw an arrow between rain and traffic in a network, if I draw an arrow between rain and traffic, that tells you that this node can encode a different value for t given each value of r. It might encode that rain makes traffic more likely. It may encode that rain makes traffic less likely. In fact, there's even a setting of the values for which it encodes that they're actually independent and you just can't tell from the graph. Because for every value of r, in fact, it's the same distribution over t. Yep. Can you have an XOR relationship between the parents and the children? Absolutely. You can have a noisy exclusive OR. Right? So like if it's A1 through AN and I want to say X is exactly one of them on, I would have a whole bunch of settings of A1 through AN, and for a bunch of them, X would probably be on, maybe probability 0.99, and for all the rest, X would probably be off. And whether it was 0.01 or 0.001 or 0.3 or whatever, now it's the details of the noise in that exclusive OR process. But yeah, and you can put deterministic things in there. If I want to say rain causes traffic, I peek in here and, well, what is the probability of traffic given that there is rain? Well, okay, it's, plus t could be 1.0, minus t could be 0. Or I could say, no, it's noisy, 0.9, 0.1. Or it's noisy, 0.5, 0.5, or whatever. Okay? So there's the topology, which tells you what relationships can exist. And then there's the actual numbers you stuff in, which are very important too. They give you things like what are the qualitative interactions. Positive interaction, negative interaction. Yes? Mm-hmm. The question is, what do you do if you have two variables? So you got A and B here. And you would like to describe a correlation between them, but there's no obvious causal interaction between them. Or if there is, maybe it feels cyclic. Well, it's going to turn out that either the arrow in this direction or the arrow in that direction gives you the ability to specify any joint distribution over those two variables. So the direction of the arrow is only going to matter when it starts interacting with other arrows. In this case, that's a very good example of why it is that these arrows are not causality. Because there are plenty of cases where you have two variables that have a non-causal correlation. Graphical models are perfectly adequate to express that, but the arrows stop sort of having this intuitive meaning, and they become a little harder to think about. That's a great question. Anything else? All right, so probabilities in a Bayes net. A Bayes net implicitly encodes a joint distribution. So I just told you what it was. It's a collection of variables, they have parents, and there's little conditional probabilities hiding under each node. They implicitly encode a joint distribution, according to the following definition. If you multiply together all of the little conditional distributions, one for each node, you're going to get the following expression. It's going to be a product over all the nodes of a probability of that node given its parents. Okay? By definition, that product of local probabilities in a Bayes net is what defines the joint probability over all of those variables. And if you squint at that right-hand side thing, it looks a lot like the chain rule. Probability of each thing given some other things. But it's not the full chain rule. And all of the variables that are missing represent conditional independence assumptions. So here's an example. Cavity causes toothache, cavity causes catch. So what is the probability of plus cavity plus catch but minus toothache? Well, I don't know, but living in this node is probability of plus catch. And living in this node here for toothache is probability of, minus toothache given plus catch. And living in the, rewind. Living under the cavity node is probability of plus cavity. Living in the catch node is probability of plus catch given plus cavity. And probability under the toothache node is probability of minus toothache given plus cavity. So I have all these pieces, and what I know is that this entry, by definition of this Bayes net, is the probability of plus cavity times plus catch given plus cavity times probability of minus tooth given plus cavity. Each of those terms lives in the Bayes net. When I multiply them together, in general, the chain rule says that's not the chain rule. Who knows what you're going to get? Look, I multiply those together at your own risk. The Bayes net comes with a guarantee that when you multiply them together, you'll get the joint. And that's because it also comes with conditional independence assumptions that we'll find out about probably in the next lecture. Okay, why are we getting guaranteed that just defining an entry of the joint, P of x1 through xn, as the product of all of the bits I have in my Bayes net, nodes given their parents, results in a proper joint distribution? Well, the chain rule says that would be okay if each variable was conditioned not on its parents, but on everything before it in an ordering. Its parents are a subset of things that are before it in any topological ordering of that graph. And so we have the additional assumption that P of each variable given the ones preceding it is equal to P of that variable just given its parents. So this is where that assumption comes in. All right. This means that not every Bayes net can represent every joint distribution. So if I give you a Bayes net that looks like A and B, I can represent joint distributions over the variables A and B, but not all of them. Just which ones? Just the ones in which A and B are independent. If I want to represent ones in which they're not, I need to throw some arrows in. All right, more Bayes nets. Here's the coin flip Bayes net, but in addition to having each variable be independent here, I also know that living under each variable is a probability distribution governing that variable's response for each setting of the parents. No parents, so marginal. Okay, that means probability of heads, tails, heads is this, probability of heads times this, probability of heads times the probability of tails times the probability of heads. Okay, so to get an entry of the joint distribution, I multiply all of the appropriate pieces of the conditional probabilities. Each variable will have one term in this product. Okay? And what's that going to be? It's going to be 1/2 to the 4th. Okay. This Bayes net here, I can fiddle around with these 0.5s. I can be like, oh, x1 always comes up heads, and x2 comes up heads 0.2 of the time. I can fiddle with these probabilities all day. I can change the joint distribution. But try though I may, I can never represent a joint distribution in which the variables are not independent. I can do one where they're not identically distributed, but not one in which they're not independent. Okay. Here's our traffic node, or here's our traffic Bayes net. It's got a node for R and a node for T. And we know that living under R, like if you say, what are you dreaming of, node R? It's dreaming of this distribution here, which is some distribution over R given its parents. It doesn't have any parents. Okay. And in this case, it reigns 1/4 of the time. What's living under node T? It is conditional probabilities of T for every setting of the parent, in this case R. And so it might be these conditional probabilities. T is off and on when R is on, and it's 50-50 when R is off. So given, armed with this Bayes net here, if I say, well, in the joint distribution that Bayes net represents, what is probability of plus R and minus T? I go through and I say, well, plus R, that belongs to the R network, or the R node in the network. And then 4 plus R minus T is right here. So I will multiply together those things, and I will get 1/4 times 1/4. Okay? Or put another way, I will multiply together probability of plus R times probability of minus T given plus R, which will be 1/4 times 1/4. Okay? Here's my alarm network. Now suddenly we have a network that's not just one or two variables, and I can compute under this assumption that I have this topology, right? The burglary causes the alarm, and the alarm causes John and Mary to call, but independently. If you just tell me the right probabilities living in each node, I can compute a probability of any event. So, for example, you might tell me, well, the probability of burglary is 0.001, and the probability of earthquake is 0.002, and here's the response of the alarm for all the different scenarios. And you're like, man, I have to say what the alarm does if there's a burglary, and what the alarm does with an earthquake, and also a burglary and an earthquake, and also no burglary or earthquake. Well, when you start giving nodes lots of parents, suddenly you have to describe what that node does in a bunch of different conditioning environments. So here it is. And you can see these are a bunch of distributions over A. Here's one distribution over A. If there's a burglary and an earthquake, 95% of the time the alarm goes off. Here is the probability of the alarm going off given just the burglary, just the earthquake, neither burglary nor earthquake. And of course, Mary and John have their own distributions, which says how likely they are to call, both in the alarm scenario and in the non-alarm scenario. These will either have to be learned from data or just supplied as givens. Right now I'm giving them to you as givens. And if I wanted to know, for example, the probability that there was a burglary and an earthquake, but no alarm, but John and Mary called anyway, I would go through and start multiplying together the appropriate conditional probabilities. And that would define the entry of the joint distribution. Okay. Any questions on that? And then we'll do a couple quick extensions and take a look at a demo. All right. So this gets to the question before of causality. What if causality is not, is not what your model encodes? So right now, this is the rain in traffic. This is the causal direction. Rain causes traffic. There's an arrow from R to T. That means living under the node R is a distribution over R. Not conditioned on anything because R doesn't have any parents. And living under T is a distribution over T. But not just one. I have to give you a distribution over T for raining and another one for not raining. And then I can use that formula, which says multiply all the entries together. That's like the Bayes-Net reconstitution formula, to take these pieces and define this whole joint distribution. In this case, the joint distribution is actually just the same size as the conditionals. There's only savings when these networks get big. Okay, so here is the joint distribution over T and R that is implied by the Bayes-Net on the left. Okay, great. So for example, if I want this entry, I multiply the probability of plus R times the probability of plus T given plus R, and I get 3/16. All right. Let's flip it around. Here's another Bayes-Net. In this one, there's a variable T and there's a variable R. There's an arrow from T to R. You're like, wait a minute, traffic doesn't cause rain. The Bayes-Net does not care whether traffic causes rain. It is a graph. You put an arrow, it's happy, okay? But when you put that arrow, you have to supply conditional probabilities. So what lives under T? Well, it used to be sort of T as a function of R, but now it's not. Now it's just T. There's some probability of traffic. And now under R, I have to specify how likely rain is given traffic and how likely rain is given not traffic. Okay, those numbers exist. Let's imagine this is those numbers. And for these particular numbers, if I use the Bayes-Net reconstitution formula and I compute every entry of, it doesn't look like an arrow, every entry of the joint distribution, it'll be this one. And if you have really good memory, you'll remember this is exactly the same joint distribution as before. So this network here, which does not match the causal process, encodes the exact same joint distribution over those variables as the previous one. Now, you might like the previous one better, and there's a lot of advantages to drawing these things causally. But mathematically, it is just an expansion of the chain rule. And P of T times P of R given T and P of R times P of T given R are both, in general, for any distribution, just going to be the joint. Until you start getting 3 or more variables, or there's no arrows, you don't actually have any claim about the underlying distribution. Okay. We're talking about causality a bunch of times. When your Bayes-Net reflects the true causal patterns, they're usually simpler. That's just a fact about the world and how we build these models. They're usually easier to think about. And they're a lot easier to elicit from experts. Like, it's way easier to go to a doctor and say, what fraction of people who have strep throat have a fever? Than it is to say, what fraction of people who have a fever have strep throat? And they're like, I don't know, there's a lot of reasons you could have a fever. And it's a lot harder to get things in the diagnostic direction, usually. If you're getting them from data, this may not be true anymore. Bayes nets don't have to be causal. Sometimes there is no causal net, so like the example you gave, or when variables are missing, often the remaining variables are kind of complicated from a causal standpoint. So for example, traffic and drips in our traffic model, they're sort of correlated by the underlying variable rain, but neither really causes the other. So either direction of the arrow is fine mathematically. And then you end up with arrows that reflect correlation but not causation. So what do these arrows mean? They might happen to encode causal structure. It's great when they do, it's intuitive, but they really encode conditional independence. They encode that when you write out the chain rule, in general, you get P of X given all the variables that precede it, but now we have P of X given only its parents. So it's a statement that once you know the parents, you don't need to know the other things that precede it. And we'll unpack that a little bit in the next lecture. Okay, so let's peek inside a Bayes net. Let's build one. All right. Let's build a Bayes net. Let's create some nodes. Let's do traffic. All right, let's build a node. Rain. I'll let it stay true or false. There's rain. There it is. All right, let's make more of a Bayes net. We decided rain causes traffic. Okay. There's rain, there's traffic. Let's create an arc from rain to traffic. Let's make some more. Let's do some more. What else was in this thing? There was rain also causes drip. My roof drips. Rain causes drip. What else? We had low pressure, right? Low pressure. Okay, and that causes rain. Okay. I've drawn a graph. In order to specify a Bayes net and thereby a distribution over these variables, I need to do more than that. I need to actually give probabilities. For example, how likely is it that there's low pressure? I don't know. Maybe 0.1. Now I need to say, how likely is it that there's rain? Well, it depends. It's got a parent. It's got low pressure. Maybe when there's low pressure, it rains 90% of the time, and when there isn't low pressure, it rains 1% or 10% of the time. Okay, I could put in other numbers. I'm just making stuff up. Okay, what lives under drip? This is the noisy specification of how rain leads to drip, or how rain causes drip. Okay, maybe 80% of the time when it rains, it drips, and it almost never drips otherwise. I didn't put a 0 there because that's just a no-no in building Bayes nets. All right, how about traffic? I need to describe the dependence of traffic on its parent. Well, when there's rain, there's 80% traffic, and when there's no rain, there's 30% traffic. Okay, I have a Bayes net. What can I do with this Bayes net? Well, I'll ask it a couple quick questions, like, hey, what's the probability that there's traffic? 39%. All right, let's get some observation. What's the probability that there's traffic given that my roof is dripping? Should it be higher or lower than 39%? Higher? Who says higher? Who says lower? Well, the suspense. Let's find out. It's higher, and that's because drip means it's probably raining, which means more likely to get traffic. Let's make another observation. Let's actually observe rain. Let's do a query. Is traffic going to go up or down now? 79 to 8. It went up a little bit. All right, here's the important one. I know it's dripping. I know it's raining. There's an 80% chance of traffic. I discover that there is a low pressure system. What will happen to my 80% chance of traffic? It stays the same. And that's because low pressure only informs whether or not it rains. And I already know it's raining. I can't know it any more than I already do. And so they're disconnected in some way, and that must have something to do with conditional independence. We'll find out what next week. Okay, so let's just stop there, and we'll see you next week for inference in Bayes nets.